So I am Dead Program, also known as Ron Evans in the real world. A couple humans call me Dad, but on Twitter, GitHub, GitLab, all the important places, I am Dead Program. And I am a technologist for hire. That is what I do. So you can hire me, believe it or not. I work at a consultancy called the Hybrid Group, where we are all technologists for hire. Just wanted to kind of put that out there. You know, whoever pays the maintainers of open source controls open source. All right, so we've done a lot of work for clients like Intel, who is also one of my sponsors. Thank you very much. And for a little company out of Boulder, Colorado called Sphero that did some robots for a movie about wars in the stars. That's all I'm allowed to say. This isn't on video, right? Yeah. But we're known for some open source projects like GoBot, which is what I did my last talk at OSCON a couple of years ago about. GoCV, which is computer vision using the Go programming language. And then why I'm here today to talk about TinyGo. So TinyGo is a Go for small places. Very little tiny places. Because everyone says that Go is too big. Have you heard that? You know, Go is too big. So let's talk about programming languages used for embedded systems, right? What are some of the typical languages that are used? Well, C. You know, no one ever got fired for recommending you use C for an embedded system. Got to keep that in mind. C++, yeah, it's just lots and lots and lots of more C in different kinds of ways. Python, having a real renaissance, a lot of really exciting stuff coming from the Circuit Python and MicroPython communities, respectively. JavaScript, a bunch of people are doing interesting things with JavaScript, like JerryScript, for example. And Rust, a language that is a little too hard for me to learn, apparently. I'm not quite smart enough. But I really like Go. And I want to use Go for embedded systems. But you said that everybody else said that someone told them that Go is too big. Well, I am going to show you right now, right this second, that Go can be tiny. So, hello world in Go, right? We've all seen, come on in, come on in. It's never too late. It's just too early sometimes. Hello world in Go. So we've seen this before. Who in here has never programmed in Go? Oh, that's awesome. All right, well, so hello world in Go. So we start with package main, which declares that this is the main module or package or unit of computation. And then we have a function main, similar to C or Python or many other programming language. This is the entry point for where the code begins. And our function main is going to do one and only one thing. It's going to print line hello world. And then that's it. So it's very similar to the kind of code you've seen in many other languages. So let's look at hello world using Go 1.12, which is the latest release of Go, versus hello world using TinyGo 0.7, which came out earlier today. I know, it's so fresh. All right, so first of all, let's say Go version. Can you guys see this okay? Okay, so Go version, Go 1.12. So let's see TinyGo version. That's version 0.70. Okay, so far so good. So now let's say Go build, which is the Go command, and we'll say that our output is going to be hello world Go 1.12, as if I've done this before. And then we're going to build for that the demo program hello world main. So the same exact program that I showed you, but stored on my local drive. Okay, so we've built it. So let's take a look at the size of that. So if we take a look at the size of this and we use ls.l, we can see that it is about 1.1 megabytes. And let's run it. And it outputs hello world. Okay, so far so good. Now let's do all the exact same things, but with TinyGo. So let's say TinyGo build. And let's change the name of the program, the output of the executable, to TinyGo 0.7 and compile the same code. Okay, so now if we look at this, we see that the TinyGo hello world is 12K. It is real. Wow. How can you do that? Everyone's like, wait, what? You must have just faked that. Well, just so happens, it's amazing the things you can do with atoms. Anybody seen this ever before? This is the smallest film ever made by IBM Research a couple of years ago, and every one of these pixels is actually an individual atom. It's not quite that small. So let's just clear up one thing right now, common misconception. TinyGo is not the exact same thing as the full Go, but you kind of suspected that. TinyGo does not support the entire Go programming language yet. Actually, as of this release, it does support pretty much all of the Go keywords. So TinyGo does not support the entire Go standard library yet. But Tiny can do a lot already, quite a lot in fact. And it's very useful for these small places where the Go standard packages are just too large. Microcontrollers, for example, or WebAssembly, or command line tools. But I'm here to really talk about microcontrollers. So how TinyGo works is we use Go itself is actually written in Go. So we use Go to talk to TinyGo to then compile with Llvm. What do I mean? So the Go compiler itself is written in Go. So since I think version Go 1.5 or so, all of Go is actually written in Go. So all of the standard libraries to parse Go and interpret it all already are built into Go standard libraries. And then there's this other thing called Llvm. So Llvm is a framework for building compilers, and it's being used by some other languages you may have heard of, like Swift or Rust. So we're just doing what all the cool kids are doing. We want to be just like them. So here's how it works. So we take the Go source code, and Go itself can then parse these to turn into Go's single static assignment form, which is kind of reducing the language down to its most minimal set. Then TinyGo takes that and converts it into Llvm's intermediate representation, which then goes through all of the usual Llvm compilers like Clang, for example, and produces an executable binary, which is highly efficient, very, very optimized, and very, very small. So the way we get TinyGo code on a microcontroller is we have a TinyGo build command, which actually compiles it for the target. We saw that a minute ago. And then we have a TinyGo flash command, which takes that code, that binary, and moves it over onto the actual chip we want to run this on. So let's start with the hello world of things, which is a blinky LED. And to do this, I'm going to use a DigiSpark, which is an Atmel ATtiny85. It is an 8-bit processor that has 8K of RAM and 16 megahertz operating speed. So it's an 8-bit processor with 8K of RAM. Okay, so let's take a look at it. Where'd my camera go? So this is a microbit, or a DigiSpark. It's very, very small. It basically plugs in to your USB. So let's go take a look at our code here. So I'm going to say make DigiSpark, and that is going to run my command, which is going to do my flashing here. So it's asking me to insert the microbit, so I'm going to put it in the slot. And now it erased the old code, and it put my new TinyGo code on there. All right. So let's go to the camera so you can actually see this. So here is the microcontroller. It's not plugged into anything. And here is a battery that I brought. So let's plug that in. And in a minute, you'll see the little blinky light start blinking. It's kind of small. So I brought another LED that's actually quite a lot larger than the microcontroller, so you could actually see what's happening. So hello world in Go, an 8-bit processor running in 8K. It is real. I have seen them. They're already here. Yeah. All right. So let's see some input and output. So GPIO stands for General Purpose Input and Output, and it refers to our ability to receive inputs by a changing digital signal, going high or low. Remember, it's binary electronics. And then to turn something on by setting it high, on, or off. Pretty much the entire Internet of Things is just turning things on and off at the right times. So to do this, we're going to use an Adafruit Circuit Playground Express board. It's a much more powerful board. It has a microchip ATSAM D21G18 processor, which is kind of very inexpensive and cool new processor. It's an ARM Cortex-M0. So it's a 32-bit processor, runs at 48 megahertz speed, and has 256K of flash. So it's really spacious. After that little tiny New York closet, this is like a full San Francisco closet. All right. So let's take a look at this is the board. It's very small. It's got a couple of buttons, a few different things built in. So let's take a quick look at the code. We're not going to go over all the code here because we just don't have time for everything. So package main, same as before. We import the machine package. The machine package is how we tell TinyGo to be able to talk to any particular hardware device. That's our hardware abstraction layer. And then we're using the time package, which is just the standard Go time package, the exact same package from the Go standard runtime. So in this case, our main program, first, we're going to set this LED equal to machine.d12, which is actually the way that the little pin on here is actually labeled. It says D12. Then we're going to tell the LED to configure itself as an output pin. That way it'll turn on or off from our command from our program. Then our button is going to talk to machine.button.A, which is there's an A in the B button. And then it's going to configure that as an input. So then for ever, because in Go we don't have a while construct. We just use for with no parameters to mean repeat endlessly. So if button.get, meaning it's pressed, we set the LED on or high. Otherwise, we turn it off or low, and then we sleep for 10 milliseconds. So we're just polling the button to see if it's pushed over and over. All right, so let's plug this in to my little USB cable. And then I'm going to push the little flash button, which sets it into the mode so I can overwrite the firmware. You'll notice that it just popped up. It's a USB device. It actually acts like a USB drive. So then I'm going to make button, which is going to compile my code, this time using the target Circuit Playground Express. And now it's been put onto the board. So if we go back to the video, we'll see that, ooh, nothing's happening. Let's go change the code here. Oh, I know why, because I have it set up for my Gopher Bot. So you might have noticed my robotic Gopher plushie that I brought with me. Well, I thought just the built-in LED was kind of boring. So I decided instead we would flash let's go to the camera. Instead, it has the same exact circuit board. So I thought, let's make this a tiny bit more interesting. Let's see how Gopher Bot works from the inside. So we're going to flash it. It's ready for some code. So we flash the code. And so now you'll notice, if we go to the camera, that when I press the button, nothing's happening. Hello. It's supposed to be turning my LED on. Oh, it's pushing the wrong button. Oh, that would help. That's the built-in LED. Well, we'll get back to Gopher Bot in a minute. All right. So how TinyGo actually knows about hardware? So there's a file format called System View Description Files. It was originally created by ARM, but it's been adopted by a lot of other vendors. It's this SVD file, which is how we're able to generate the wrappers that actually know how to talk to the actual hardware itself. For example, here is this wonderful XML format for an NRF51, which is the microcontroller that's built into a BBC microbit. And so you can see it's kind of a rather frightening format that's describing these things having to do with the base address, which is where the GPIO, where the turning the pins on and off is located. So we take that and we use it to generate some Go wrappers to turn it into Go structs. And then this very, very low level interface is what we can use to then turn pins on and off, read whether the buttons have been pushed, etc. So let's see how the actual Gopher Bot itself works. So we actually wrote some code for crowdfunding campaign for the Gopher Bot, which is some slightly higher level wrappers, because the idea here is not to just write simple code that flashes LEDs, right? It's to write some kind of application that actually does something. In this case, a robotic gopher plushie toy. Very, very important. So I showed you already that it's got the same circuit board. So we wrote a package called the Gopher Bot Package, which is we're providing to people. Basically, it's just open source, so if you want to get the parts, you can build your own. Or if you missed the crowdfunding of the kit, well, too bad. Sorry, it's over. But we're using just regular Go code. So in this case, we're going to control the visor. We have a green mode, red mode, Cylon mode, and Christmas mode. Maybe we'll reopen the campaign for Christmas. I don't know. We'll see. And then, so we're using the Mqtt, which in Go is how we start an enumeration from 0. So green visor 0, red visor 1, Cylon visor 2, etc. And then we're doing the same thing with the buttons to be able to go forward and back. So our main function, the first thing we're going to do is say antenna is equal to the Gopher Bot's antenna. All that is doing is the same thing we saw in the first demo, right? It's just referring to the pin for the antenna. Then the left and right buttons, which this time I will have the right pin for the Gopher Bot. You saw that it was working just on the bare CircuitPython board. And then the Gopher Bot visor. So the Gopher Bot visor is a series of programmable LEDs that are called the WS2812s, and they're really, really commonly used. Adafruit, great company out of New York that makes these boards, sells them under the brand name NeoPixels, and you've probably seen them called that, but there's also other more generic 38 or WS2812s, like the ones I use. So first thing we're going to do is say go antenna.blink. So in the Go programming language, when we say go and then a function name, it starts a Go routine. So this is actually going to concurrently be blinking our LED while everything else is going on. Okay, yes, Go concurrency in full action. So then, repeating endlessly, if the right button is pushed, we're going to increment the mode by 1, and if it goes past the end, we're going to start at the beginning again with the green visor. Same thing with the left button. If it goes past the beginning, we'll go back to the end. And then based on what the mode is, we'll set the visor and then sleep. So we're just polling for the button. All right? So far, so good. So make Gopher Bot. Plug back in the Gopher. Double click the button so that it's ready for code. And then flash it. All right. So you'll notice the blinky LED is now blinking. It's on the end of a spring. That way you can go boing. Very, very important. And you can also tell here that I can control the visor by pushing the buttons. So if I push the right button, now it goes to the Cylon mode. Whoops, we lost an ear. Cylons don't feel it. Or do they? The Christmas mode. So you can see that we're using slightly higher level APIs that we've built just on top of the core TinyGo APIs for the low level hardware. So yes, you can use it for toys. All right. Oh yes, thank you, thank you. So this is the time for our ever popular choose your own hardware adventure. What am I talking about? Well, you could take home some cool hardware to actually start playing with TinyGo on your own. Yes. What do you have to do? You just have to go to Twitter and tweet using the hashtags TinyGo, Arduino, and OSCON about why you should win. So what is it that you're going to win? Well, one of the brand new awesome Arduino Nano33 IoT boards, which is actually what I'm going to use for my next demonstrations. Let's take a look at one. Unplug Gopher Bot. We'll call on you later. So these awesome boards were donated by Arduino, which was one of our sponsors, and we just made some big announcements with them today of TinyGo powered by Arduino. So that's what I'm going to use for my next demonstration. So just remember, tweet using TinyGo, Arduino, and OSCON. For example, I will save the world using TinyGo running on an Arduino OSCON. Or I just want to make something blinky. You know, some justification. Like, I'm going to give this to my kids to teach them how to program. Give me that, kid. You don't know what you're doing. Oh, sorry, son. Sorry. All right. So let's talk about the Internet of Things. So it's only a thing unless it's got internet. Pointed out one of my clients a few years ago. And, you know, it seemed at the time, you know, sort of silly, but it really stuck with me as sort of a pithy summary of, you know, everything that's either right or wrong with the device, depending. Now, Gopher Bot has no connectivity because it turns out, I believe, what you want is programmable toys, not connected ones. Right? You want to be able to program them, but you don't need your toys to go on the internet. There are some things that you do want to go on the internet, however. So, Internet Protocol, IP, the world is built on IP. We need it. We can't do anything without it. Everything uses it. And the Go standard library, one of the reasons a lot of people use Go, the programming language, is because there's really, really great networking support built into Go. So wait, Dead Program, are you saying we can just use Go's net package, the networking stack of Go, we could just use that in TinyGo? Not yet. But we do have a very large number of compatible interfaces. Since Go, a lot of the design pattern of using Go, even though it's not object-oriented, you can still define interfaces. And if you implement those interfaces, then it's considered to be an equivalent object of that type. So we have interfaces for a lot of net, and we also have compatible interfaces to allow us to use the PAHO Mqtt adapter. That is the official Mqtt client library, which is maintained by the Eclipse Foundation, and that's what most Gophers use as their client software to be able to talk to an Mqtt message broker. So let's take a quick look at an Mqtt sensor station that uses the Arduino Nano33 IoT, an LED, and a button. And it's based on the Arduino Nano33, which is the same chip as the CircuitPython, right? The exact same SAM D21, same specs. But in addition, it can be used to connect via UART through a serial interface to a built-in U-Blox Nina W102. That is a dual-core extensa. It's a 32-bit processor, and it's the same processor as the ESP32 Wi-Fi chip that is very, very commonly used. That's actually on board this same board from the new Arduino. So here's just a quick picture of what we're going to see. We got the Nano33. It's got the main processor, and then we're going to connect to the Nina W102 for Wi-Fi. Then we're going to use that to connect to our Mqtt message broker. All right, so here's the code. Well, actually, before I do that, let's just very quickly make sure I'm connected to my device. Create a new Wi-Fi network using my Rando adapter. No, not that one. No, we'll just use this one. No, I don't want to use this one. Let's see here if it's plugged in. Might be plugged in, might not be plugged in. Let's see, I have to make my own network here because, you know. Ah, yes, here we go. Yes. Make my new Wi-Fi connection. Create my access point. All right, so while that's thinking about doing that, so let's look at the code. So package main, same as before. This time we're going to import a few other packages. The machine package, again, so we can talk to our hardware. The math rand package, which is to create random numbers. That's part of the Go standard library. Time package, same as before. Now we're going to pull in a couple of drivers. So TinyGo has a separate repository with low-level hardware drivers for sensors and other devices, and that's where we have our ESP-AT. The ESP chip is talked to with an AT command set, just like an old Hayes modem would. And so then we also have our Mqtt adapter built in there. So I have my access point, not with this SID and password. It's going to connect to the access point I mounted here. And I'm just going to have it communicate with an Mqtt message broker running on my local machine because I don't have proper internet. But I could be using a TCP or an SSL secure connection to talk to any message broker as long as I do have connectivity. So we're going to use the UART1 because UART0 is going to be connected to my computer. UART1 is connected to the Wi-Fi chip. We have a couple of pins for its transmit and receive. And then we're going to use the SPAT adapter. So what we're going to do is we're going to configure our UART so we can talk to it, get a random number so I can make up a client name that's unique every time that my client connects. We've got our button, the button we're going to push in order to send a message. And then we've got two LEDs. The ready LED, which says, yes, this IoT sensor station is ready to start transmitting. And then a send LED, which is going to blink every time we actually send a message. So the code that we're going to do, we're just going to kind of go over it very quickly. We create a new adapter saying spat.new, and we pass it the serial interface that we're going to use. That way, whatever serial interface that happens to be connected to our Wi-Fi chip, we can use that. So then we are going to connect to the Wi-Fi chip. And if it's ready, we're going to turn the ready light on and off real fast. Then we're going to create our client options for the MQTT broker. If we're going to use a secure connection, this is where we'd pass some of the TLS info. And then we're going to say, add the broker information in this fashion. This is the canonical code that you will see if you look at the Eclipse Foundation's PAHO library. This is the exact same code. This is just standard Go. So then we're going to create a new client and connect to it, wait for the connection, and if there's an error, we're going to just fail and display a message through our serial port. Otherwise, we'll turn that ready light on, and then every time we press the button, we're going to turn on the send LED and then publish an MQTT message to our broker. And then we just keep repeating. We'll turn the light off again after the message is sent. That way we know it actually worked. And then we have a couple of helper functions that are not that important here, just to simply understand that this is the process that's happening. All right. So let's plug in. Hopefully the cables are all still connected. We'll plug it in, double click the little button so that now it's in the mode necessary to receive our code. And then let's say make MQTT sensor. This uses a different flashing, use something called BASA, which is a command line utilities that are provided by Atmel in order to flash their chips. And so now it's flashed. All right. So let's unplug it. Let's plug it back in and reset it. So now this is the LED. It just flashed once. So it's trying to connect to the Wi-Fi access point. Then if the demo gods favor me, then that light should come on as it's able to connect. Yes? All right. So then every time I send an MQTT message, that light will flash. Well, yeah, how do you know it's working? Well, let's go to our MQTT message broker and see the messages come in. So there's the messages. They're coming through in a JSON format that's known as SenML, which is sensor markup language. It's the same markup language that's used by Amazon Web Services, and a lot of other Microsoft IoT uses it. The other things I can't talk about yet use it. So it's kind of a standard for ingesting sensor data. So yes, so it's really working. I could be plugging it into my battery, but we don't have time to go through all of those little things. But I think you'll believe me when I say it's using the Wi-Fi. So yes, the Internet of Things, it's real. All right. This is fun so far. So let's build a little flight controller out of the Arduino Nano33 IoT, an analog joystick, an OLED display, and some buttons and the UART. Wow, that's a lot of moving pieces. You haven't seen anything yet. All right, so here's a quick diagram of what we're going to see. So we have two different kinds of input. We have analog input from the joystick. We have GPIO input from the buttons. That way we can push them. They're going to be going into the Arduino Nano33 IoT, which is then also using an I2C interface, which is a digital protocol to talk to the OLED display. All right? And so here's the code. We're just going to go over it very, very quickly. We don't have time for everything. Same idea, though. We're importing image color, which is just one of the Go standard packages for representing color. Machine package for our hardware abstraction layer. Stir, conv, and time, just part of the Go standard package. So here we have two packages created by one of our contributors, Conejo Ninja. the TinyDraw package and the TinyFont package, which are very, very small fonts and primitive drawing that we can use on all of the different displays that are currently supported by TinyGo. If any of you saw my little name badge, that's one of the supported platforms, and that's how we did that. And then we're going to use from the TinyGo drivers repository, the SSD1306, which is a small OLED display. Let's go to the camera real fast so you can see what this actually looks like. So here's the display. Here's my analog joystick. Here are my buttons, and buried away beneath cables is my Arduino. So our main function, we're going to initialize our display saying machine.i2c0.configure. So it's going to configure the I2C bus on the chip. And then we're going to say go handle display, because all of our display refreshes are going to happen asynchronously inside of a Go routine. So yeah, once again, we can run concurrency, even on microcontrollers. So we're going to initialize the analog to digital converter so we can read the joystick, X and Y direction. And then each of the buttons, when we push the button, things will happen. What happens? Well, we're going to display what happens by putting little filled circles for when you push the buttons, and then numbers that appear for each of the different joystick X and Y positions. And then we sleep, so every 100 milliseconds is when this is actually going to happen. That way we're just polling. This is a very common pattern that you see in microcontrollers because everything happens very, very quickly. All right. So if we say mic flight stick, and we plug it in, same as before. Then I'll double tap the button, same as before, to put it into the mode, ready to receive the code. We compile and we flash it. And okay, we're ready to go. So let's go to the camera. And you can already see the display here. And as I move the joystick right, you see the X and Y changing. The bottom is the lowest Y, highest Y, right and left. And if I push the buttons here, you'll see the little display changes. Because I just can't use a normal DualShock controller. I need to build my own flight controller and program it. Because my kids won't let me take their controllers anymore. They're like, Dad, that's it. You're done. I can understand that. And what's happening here is it's actually just sending the serial data to the computer. That way, when we actually fly the drone in our next step, that's how the messages get there. Wait, what did he say? Fly the drones in the next step? Yeah, that's what I said. So now let's look at the full application. How are we doing on time here? Yeah, we're good. All right, so let's look at the full application. That way you can kind of get an idea of really the full end-to-end solution. So it's a flight system that uses the flight controller that we just programmed and flashed, plus a computer vision-based ground control system and a Tello drone. So for this, we're going to pull in our old friends GoBot. So GoBot is going to talk to the DJI Tello drone. The Tello drone is a really cool drone that actually, among other things, it's actually built on the Intel Movidius 2 neural compute chip. So I happen to have one in the form of a USB drive. So this is actually a special kind of processor. It's a RISC processor designed for massive parallelism, and it's a really great chip for offloading deep learning applications of deep learning, not the learning part, not the training, but if you've got deep neural networks, this is able to do a lot more computation per watt. You know, there's already a solution for that. It's called a GPU, but it's got a 45-watt power supply that's heavier than the flying object. So this DJI Tello drone has one of the chips that's in this built in, right? Because this is just a USB form, so you as a developer can actually develop. So once you finish your product, then it can actually turn into this. So let's turn on the drone. So it's going to boot. So while we do that, So then we're going to use GoCV. So GoCV are Go wrappers around OpenCV. And so the video that's going to come back from the drone, that's how we're going to get it into our code. And for that, we're going to use GoCV's compatibility with OpenVINO. OpenVINO is just a version of OpenCV with some special hardware acceleration. That way we can take advantage of the Intel chip. It's also all open source. So here's the architecture. Same thing we did before, right? The flight stick, except the UART information is going to go to the GoBot program. The GoBot program is going to use UDP to talk to the Tello drone. And the Tello drone is going to feed back using UDP, the video, so we can actually see what the drone sees. Sounds very complicated. So here's the program. We're just going to, this is the GoBot program. This is not the TinyGo program. We're just going to look at it, just a part of it very quickly. We pull in a whole bunch of standard packages from Go. Sync atomic being a very important one, because this is how we're going to synchronize the commands coming from the joystick, sending them to the drone. There's no drone that can respond as quickly as you can button mash, right? You don't want that to happen. Instead, you want to attenuate the controls coming from your controller so that instead your drone remains stably in flight and does what you meant, not what you did. That's kind of hard. So then we're going to pull in a standard serial package. And then we're going to connect to the Tello drone on port 8890, UDP port. That's how we're going to send the commands. And then in a Go routine, we're going to process the joystick events, grab the video using FFmpeg, stream it to the drone, and then based on that, we're going to, let's look what the controls are. This is kind of important. Button 1 is the CV system, 2 is land, 3 flip, 4 takeoff. Okay, that's enough. I could do this now. All right, so let's see. First of all, let's make sure the drone is on. Drone is on. Let's put it down here, because drones fly generally, hopefully. All right. So here I got the flight controller in my hand-ish. Well, I'll just pick it up once I run the program. All right, so now we're going to run TinyGo. Oh, wrong tab. All right. Make TinyDrone. So if the programming gods favor me. Oh, there's one thing I forgot to do. Connect to the drone. It doesn't work unless you do that. If it did, it'd be really frightening. It only has about 8 to 10 minutes, so if you could stay away from it that long, you're fine. All right, so we're connected. There's a very nice view of oh, it's detected a human already. Oh, I think I have it backwards. Whoop. Oh, I guess, well, no, there we go. All right, that's all right. I'll just reverse my posture. That should be okay. So yeah, it does all the usual drone things like flips. A flip to a drone is like a lens flare to a photographer. Something that they say you shouldn't do in school, but you do them anyway. And so yeah, it's actually a lot more responsive than the DualShock. Hello, fellow. Hello, friendly humans. Do not run. We are your friends. So yeah, I could do this all day. I love flying drones. But I'm a really bad pilot, but I'm really good at writing autopilots, turns out. So yeah, it's got good range. So yeah, this is so yeah, feel free to tweet something about how awesome Intel is right now, just because they made this possible, really. And so yeah, let's bring it in for a landing before something goes wrong. That's usually a good idea. Well, let's just do one more flip before we do. Okay, I've definitely pushed it as far as this sanity would allow. All right, complete end-to-end solution. Wow, that was actually kind of amazing. So let's talk about the future of edge computing. Anyway, wait, that wasn't the future? No, that's the present. Let's get to the future. I love the future. I live in the future. So WebAssembly. Who here has looked at WebAssembly at all? All right, who here has even heard of WebAssembly? Yeah, you can't avoid it. It's like it's everywhere. So WebAssembly is very interesting because it is sort of a way to compile in a device-independent way. And it turns out that Llvm has really, really good support for WebAssembly. So we thought, wouldn't it be cool if there was a TinyGo playground, if there was a website that you could go to and you could compile your TinyGo online like all the other cool kids are doing these days? Because, you know, we're like cool. So yeah, we have put that live earlier today. That was one of our 3 big announcements. It's online right now at play.tinygo.org. And so let's take a quick look at it. So I don't know if I have internet, but maybe I do. Oh, yeah, I probably do. I can run it locally, but this really proves it. All right, so here's the TinyGo playground. And a lot of the people are using it. I think it was on Hacker News, so it might be taking a little longer. There's a whole blog post that my colleague Mqtt wrote about how this part works. It's actually using serverless calls to Google Cloud Runner, because every time a compile job is happening, we're using a Docker container. So that way we can scale. As long as somebody pays the bill, then we can just keep going. So you can see this is just regular code. Let's just say, hello, TinyGo friends. And so it compiles it on the fly, using the GCR, and hello, TinyGo friends, how are you? So yes, we're actually compiling to WebAssembly and then executing that inside the browser. Okay, so that's pretty neat. That's pretty neat. But we can also have a board simulator. So if you want to see what like a Arduino Uno would do, you notice how the little LED simulator here is blinking? So if I change those numbers, let's make it do it every half second. It'll compile, and now you see it change the time of the LED. So it's actually executing the WebAssembly against a board simulator running in the browser. Okay, that's pretty neat, because it means that we can write more sophisticated simulators for other boards that have, for example, more LEDs. Or like my badge, a little simulator for the e-paper display. But I don't want to talk about that, because I want to talk about something even more exciting. So RISC-V is the future's future. Anyone here heard of RISC-V? So RISC-V does to processors what open source software has done to pretty much every category of software. It actually provides an open source reference platform, instruction set, and hardware design so you could build your own chip, your own processor. And so I have a Sci5 Hi5 Rev B board. This is a extremely hard to come by. Never mind what I had to do, who I had to beg. So it looks very much like a classic Arduino, but you can see that it actually, these are all the support chips. The actual RISC-V processor is that little tiny thing right there. Okay? So far, so good. So what we have experimental support for compiling to RISC-V using TinyGo. But more, we also have that same support on the TinyGo playground. So if I write some TinyGo code and I click on this flash button here, it's actually going to compile my TinyGo code and then download a hex file with the binary. So let me plug in. Let me go to the camera here. So I'm going to plug in my Hi5 RISC-V board, the newest of the new, so new that no one even has one. Even I barely have one. And because it really acts like the same as the other drives, it just mounts a USB drive. So you'll see it, here's my high five. And then let's go to my downloads where my code that I downloaded before, it's one of these. It's probably the one with the highest number, let's guess. So if we just drag and drop it, it flashes the code. And if we go back, you'll see, whoops. You'll see we have a Blinky LED on a RISC-V board that we actually compiled it online using the TinyGo program and downloaded it. This is next year's demo today. That's why I haven't gotten out much lately. All right. Wow. So the future is here now. We just need you to join in. So go on Twitter. Please tweet about that stuff. You can win one of those 3 Arduinos. We'll do that right after the cleanup. TinyGo.org. We just shipped our 0.7 release. I think we have about 25 contributors. We have over 3,000 GitHub stars, but more important, the number of contributors. That's a lot more interesting to me. We just need you. So join the evolution. It's already here. And I think I have time for a couple of questions, yeah? Oh, well, yeah, everybody wants to win something. Like they're like, wow, I can get one of those Arduinos. They were out of stock when I tried to order them. So, yeah, any, yes?
So how does the thing garbage collect on the more constrained platforms?
So the question is, how does TinyGo garbage collect on more constrained platforms? So we actually have several different garbage collector implementations that we've written. We have like a simple one that's just a basic mark and sweep type one. We have another which allocates but never deallocates. And then we have one which doesn't allocate and gives you a warning, which is very useful if you want to write a Go program that does not require any garbage collection because everything's already pre-allocated. That's a little bit more of a traditional way to write microcontroller code. Is not actually do any type of allocation at runtime at all. But we do allow it. It's not as efficient in some ways as Go is built as the main Go implementation garbage collector. That is a little bit smarter as far as randomly deciding which thing to collect. We have a much simpler implementation, but we're working on it more. And also, our basic garbage collector now runs in WebAssembly as of this release. So give that a try and see what happens, because we need your bug reports. Yes, you, sir.
Do you support ESP32 now?
So the question is, do we support the ESP32? Not exactly. The Llvm backend support for the ESP32, they have some commits that just landed in the mainline Llvm repository, but I don't think it's a complete implementation, and those commits just landed like in the last couple days. So we will have TinyGo running directly on the ESP32 very, very soon as those changes make it into the main Llvm core, because we'll just be able to set it up as another target as we have the other platforms that we've supported. Right now, we're just using it strictly as a Wi-Fi or BLE connected peripheral. Any other questions? So I have a lot of stickers. So you could take those back, and after I pack up my stuff into my case, then I will give away the free items. So I thank you very much. I am Dead Program Technologist for Hire, and welcome to the world of TinyGo.